Welcome to Fun to Learning of Technical Knowledge. This is Memory ECC, the comprehensive of SEC-DED. This is a one-day short course. Here, we are share out the academic contents. This course is prepared by Dixon. We want to close the gaps between academic and industrial practice, that not taught in college or university. This course is arranged in 3 sections. First, we will learn about the theories of DRAM ECC from academic perspective. Then continue smoothly to industrial 64-bit plus ECC implementation. Last section is discuss about where is bit flipped error occur, and it causes. Let's start with introduction of memory controller ECC for DRAM.
Legacy memory modules are with just enough DRAM ICs for memory bits capacity. Due to signal noise, or electromagnetic interference to circuit, or DRAM IC internal defect can cause a single bit to spontaneously flip to the opposite state. The mission-critical computers that cannot be tolerated data corruption under any circumstances needed error detection and correction, EDAC. The solution is memory modules are designed to carry extra DRAM IC to store parity or check bits, and the memory controller add in error correction code, ECC mechanism. Here is example of ECC memory in DDR3 DIMM. Each of DRAM IC has 8 bits wide data bus. Total up 8 units of DRAM became 64 bits wide memory bus. Additional DRAM IC will store 8 bits of ECC data. Some of computer systems are built the ECC memory on the same PCB motherboard together with processor. This is to shorten memory data path, protect data bus from signal noise, and no mechanical connectivity issue. However, it's lost the memory upgradability. The most common computer error correction code is a single-bit error correction and double-bit error detection SEC-DED Hamming code. Modern processors are mostly integrated memory controller into one IC. The 32-bit processor with 32-bit memory data path width, plus ECC is commonly using 3932 SEC-DED code. The 64-bit processor with 64-bit memory data path width, plus ECC is commonly using 7264 SEC-DED code. The 64-bit processor working in 32-bit compatible mode is mostly half 32-bit set to 0, either high 32 or low 32. Just now, 9 chips DDR3 DIMM, each DRAM ICS has 8-bit data width, so a total of 64 data bits will be transferred. In addition, the extra ECC chip will output another 8 bits, making the module 72-bit wide.
Now, let's study the Hamming code.
Hamming 7/4 code used in telecommunication, were invented by Richard Hamming in 1950, during work at Bell Telephone Laboratories. It encodes 4 bits of data into 7 bits by adding 3 parity bits. It can detect and correct any single bit error. In example, P1 covers D1, D2, D4. P1 is generated by XORing D1, D2, D4. P1 provides an even parity for bit location 1, 3, 5, and 7. P2 covers D1, D3, D4, P2 is generated by XORing D1, D3, D4. P2 provides an even parity for bit location 2, 3, 6, and 7. P3 covers D2, D3, D4, P3 is generated by XORing D2, D3, D4. P3 provides an even parity for bit location 4, 5, 6, and 7. The general Hamming algorithm generates a single error correcting code for any number of bits. First, arrange bits position starting from 1, bit 1, 2, 3, 4, etc. Second, all bit positions powers of 2 are parity bits. Third, all other bit positions are data bits in sequence. Last, each data bit is covers with parity bits of its binary form position. Highlighted blue bit are used to generate of respective parity bit. Overall, M parity bits can be cover bits from 1 up to 2 power m-1. In example here is Hamming 3126 code. The way to generate Hamming 3126 code parity bits. Parity bit 1 is XORing data bits in highlighted blue boxes. D1, D2, D4, D5, D7 etc. until D26. Parity bit 2 is the same XORing data bits in highlighted blue boxes. D1, D3, D4, D6, D7 etc. until D26. So on for another 3 parity bits. The Hamming codes are able to correct single bit error. It is calculate the syndrome bits. Syndrome bit 1 is XORing parity bit 1 with data bits in highlighted blue boxes. P1, D1, D2, D4, D5, etc., until D26. Syndrome bit 2 is the same XORing parity bit 2 with data bits in highlighted blue boxes. P2, D1, D3, D4, D6, etc., until D26. So on for syndrome bit 3, 4, and 5. The binary syndrome bits, SB5, SB4, SB3, SB2, SB1, result tells the position of the bit flipped. From the M parity bits can be cover bits from 1 up to 2 power m-1, the possible Hamming codes are listed as per table. The ECC algorithm uses Hamming 7264 code SEC-DED algorithm. It is a truncated from Hamming 127-120 code, plus an additional parity bit, which has the same space overhead as a 9/8 parity code. Hamming codes with additional parity to make it as SEC-DED. Let's understand the basic concept of parity check with 9/8 code. To encode for parity bit. Parity generate by X or 8 bits logic depth. To decode this parity check. Total 9 bits are XORing to obtain an output result, even, 0 is no error, odd, 1 is found an error. Continue from previous Hamming 3126 code. Add extra parity bit to calculate all 31 bits from Hamming 3126 code. This is used to detect the double bits error. The Hamming 3226 code became SEC-DED. To visualize the Hamming codes with additional parity coverage, we use Hamming 8.4 code. It is Hamming 7.4 code with extra parity bit. Parity bit 4 is XORing all parity and data bits. P1 to D4. Hamming 7264 SEC-DED code is a truncated from Hamming 127-120 code plus an additional parity bit. The single bit error correction, double bit error detection function is working perfectly. However, the parity or check bit for each row is X or different number of data bits. In example, CB1 is generate from X or 35 data bits. CB7 is generate from X or 7 data bits. And the most bits, CB8 is generate from X or 71 data and parity bits.
What is the Hamming code optimization?
The original Hamming 7264 code SEC-DED advantage is error code, syndrome bits, is straightforward, with binary pointing to error bit position. However, it is not constant X or length of logic depth for each parity bit, or check bit. This is meaning more complex and more transistors to design ECC encoder and decoder. It may take more clock cycles to generate output. Anyway, there is an example of implementation at Xilinx product. We will discuss it later. First 7264 SEC-DED code optimized by M.Y. Shao in 1970. It is constantly X or 26 bits logic depth for each parity bit, check bit. It is simpler to implement at silicon with reduced gates count. An example of implementation at Lattice product using Shao parity check matrix of the 7264 SEC-DED code, version 1 as showed here. The Shao constructing optimal odd weight column criteria are: first, there are no all zero columns, or all one columns. Second, every column is distinct. Third, every column contains an odd number of ones, here is odd weight. In addition, analysis found also maximize using the columns odd weight 3 or 5 of ones, and no odd weight of 7. Using similar Shao optimal odd weight column criteria. Marvell has its own 7264 SEC-DED for Armada XP series ARM processor. Intel also has its own 7264 SEC-DED for 7th Gen 64-bit x86 processor.
This is end of section 1 in ECC theories. In section 2, we discuss about industrial 64-bit plus ECC implementation for 4 types of Hamming code, or Shao code by 4 semicon companies. Then, we share some great details of how to manually decoding double bit and triple bit flipped from real case studies.
Now, we will discuss on how to decode multiple bit ECC error. I used 2 real-life Linux OS memory ECC test case studies to explain it. The Linux OS run on Marvell ARM v7 SoC that explained earlier. These are output from memory stress test program, after encountered multiple bit failure. From SDRAM error address register, the error type is double bit or multiple bit error. From received ECC register, expected ECC code is all 0. From calculated ECC register, the ECC is as showed. This case study 1 finding is D28 and D6 are both flipped bit. We can add in another row of ECC calculation to verify this finding. The result is ECC calculated output is all bits 0.
In last section, we share the science facts of where is bit flipped error occur, and what causes it.
Research has shown that the majority of one-off soft errors in DRAM chips can occur from background radiation, mainly cosmic ray and its secondaries. An example, the spacecraft Cassini-Huygens, with built-in EDAC, and telemetry reporting that launched in 1997. During the first 2.5 years of flight, the spacecraft reported a nearly constant single-bit error rate of about 280 errors per day. On November 6, 1997 with solar particle event, this is confirmed by the GOES-9 satellite, the number of errors increased by about a factor of 4 in single day. Here is the short explanation of single event upset. Boron is p-type dopant, for transistor junction formation. Boron has two isotopes, B10 and B11. B10 is unstable state. When cosmic ray neutron hit the boron-10 nucleus, it will causes the nucleus split into two parts, lithium-7 nucleus, alpha particle, and generated gamma photon. These particles could fly through junction gate and created ion track. The ion track charges will try recover and stabilize by itself. However, some charges will remain scatter distributed inside silicon, and causes some soft-type electrical failure. The main reason for SCU affected mostly DRAM is due to DRAM function is designed to store charges as the signal. However, any silicon junction could be affected by the same soft-type failure effect.
Thank you, and have a nice day.